Hello? Okay, let's get started. Any questions so far? No? Are you still with me? You sure? No? Professor? Yes.
When will be the first conference?
Good. So did you guys had already survey or no? Oh, you did? I didn't know. So do you know the result? No. So anyway, it shows up out of the 3 options next week, yes? Tuesday, Thursday, Friday? Okay. That's a question that I don't have an answer to. So let me look it up and tell you. Who cannot come on Tuesday evening, 7? Or who cannot do on Thursday evening? Who cannot do on Friday evening? Oh, okay, like absolute sense. Okay, let me do it again. On Tuesday, I can do okay, I cannot do Tuesday. 2 are there. 1, 2, good, like absolute sense. Thursday, who cannot? Like absolute sense. Friday, great. So what does that mean? Let me think about it. Okay. So, all right, let's do it. So today we will discuss, I think I started talking a little bit about the crossing last time, or I didn't quite finish it. So I will finish the crossing and then CPT symmetry or CPT variance, and then we'll start construct differential transition probability. So probably we are not going to finish today, but probably by next lecture we will have cross-section decay rate in hand, so we can actually compute now something that experimentalists measure. I mean, experimentalists measure all kinds of different kind of observables, not just cross-section and decay width, but they can measure a lot of quantities. Well, these are the 2 most important things. All right, so let's first talk about crossing. And then we're going to talk about CPT. So we're going to talk about this together. CPT invariance, so CPT 0, CPT symmetry. So to settle the crossing, let's recall ourselves the following process, for instance. So we talked about this type of process, right? So we went through all these kind of processes. And then, for instance, if I do this, this can describe n pi goes to n pi process, right? We talked about that. Or if I read the diagram that way, we can describe pi goes to n bar, for instance. And you can read the other way around too. So we talked about that. Now, we also understood like there are 2 characteristics. Like we talked about direct, you call up potential line. Okay, and then we also talked about like cross, you call up potential line. And in this category, just to summarize, we saw a feature that this behaves like 1 over r e to the minus some length scale r divided by capital R, where capital R was the range parameter of the first. And then depending on the math degeneracy, whether they have the same math, or we also look at a process like that. And in this case, obviously the math are the same. Depending on that, we saw that either this is such a constant, regardless of energy range we use, or it can be energy dependent range and so on. Then we also talked about pole length. So in this case, it happened when we look at this S-channel diagram, and we can actually produce something, and we talk about all this. Now, the crossing states that at least for these 2 processes, like pi n goes to pi n, pi goes to n, or n goes to pi. they look very different physics, but it comes from a single, the same function of complex momenta. Okay, so you just need to look at the correct regime in the complex variables. So in order to set up their crossing, let's first talk about crossing. Crossing symmetry in literature usually say, but as Konna said, it is really, if you like, slightly more proper way of saying it's crossing property. In the sense that this is not a symmetry of like quantum field theory. This is a property that that a finite amplitude, okay, finite invariant amplitude enjoys, which we you will see exactly what I mean. To set up this thing, let's consider the following situation. So first we have a whole bunch of, it doesn't need to be only two, but I'm just gonna focus on 2 to 2, just for the sake of concreteness. We're gonna focus on these cases where I have 4 possibly different kind of particles, or 2 of them can be the same, like in this case, and so on. I don't care. So I'm pretty agnostic here. I'm not specifying which ones are the same, which are not the same. I'm also taking all the momenta inward, going towards the vertex or interacting points. E3 equal. Once again, you don't have to just look at the 2 to 2, but you can look at, you can look at a lot of other like there. So this is generic thing. Okay. Now I picked all the momenta going in, and I have to talk about that thing first. So to recall that, let's recall the following facts. So the quantum field. Okay. So let's actually use the complexity to illustrate the point. Recall the following fact. So there is a complex scalar. In the normalization that I used to use this vector, it looked like alpha p to the I p dot x, beta p dagger is the plus I p dot x. And then own shell is those. Okay, so we used to use that. Now, one thing that I want to say is the following. So, so the relation between these two terms. So what this says is that you have to sum over all possible 3 momenta. That's what this term is, right? With some normalization. So you're gonna sum over entire 3 momenta. But for fixed 3 momenta, okay, for any fixed 3 momenta, there are 2 terms. And these 2 are related by the fact that I'm just basically going back and forth between 4 momenta being shifted, like negated like that. Okay, P2 minus C or vice versa. If you look at it. But again, when you do that, the 3 momenta doesn't change. Like in other words, what is the interpretation of this first term? What is the interpretation of this first term? You can annihilate the particle. So in this case, it says that you can annihilate particle with some energy which is positive, meaning physical, and then some fixed 3 momenta, and then phase appears to be with the minus sign here. And then in this case, it says that you can create, I'm just repeating all you know now, which is great, for any particle on the other hand, but then with also physical energy, the same 3 momenta. But then what's the difference between the two? Obviously, I said that first is, but then when you do that, likely what you would feel is that, oh, here it looks like energy is negative, right? So if it's zero component here were positive, obviously the 0 component here would be negative. Also, super naively, you might say that if here if 3 momenta is p, x, by which I mean this vector, here it looks like that 3 momenta should also be minus of the p vector, right? Not just p, but I said it's the same p. So let's try to understand that slightly more carefully. So to understand this slightly more carefully, let's consider about the following calculation, which you have done it. So I'm just gonna put it. Imagine that you had a particle, incoming particle, with say p coming in towards the vertex, like that. So we look at this kind of computation. So if I look at this with this stage, there's incoming state. Then in this calculation, you're going to pick up the contribution from alpha. Okay? Because this can be represented as creation cycle on the vacuum, you have to pick the Gonell operator to have non-zero. So then I have done this calculation, let me just write down the answer. So e to the minus idea. So what is the physical interpretation? Well, this represents the incoming, meaning there is a particle that going towards the vertex. Yeah? Okay, so then let's consider the following. Okay, let's consider the following this thing that ended on this. So if I do that on the other hand, so if I look at this instead, then I have to use creation operator, right? To get the non-zero answer. So in this case, I have to use the beta dagger, and you're gonna get plus I beta x. So let's actually say the meaning of this thing. So what I have done is that if you just look at this wave function, the difference between the two is p for momenta replaced by the minus for momenta p. But the result of that is that here it is an incoming particle with a 3 momenta p. But here it is an outgoing antiparticle with the same 3 momenta p, because I'm looking at the state with the same fixed 3 momenta p. And another way of seeing why, even if I flip this order, they correspond to the same 3 momenta p, you just look at the following things. If you look at the minus I or plus, doesn't matter. If I have p dot x, what do you get? You get either plus minus I et minus p vector x vector. Okay? So if you imagine that this is some sort of a sinusoidal function, then the peak of that oscillatory behavior is controlled by the fact that et minus beta x equals to 0 point. Imagine you have some sort of cosine potential if you like. Okay? So for this, let's consider cosine of beta et minus beta x. Okay, but this is 0, that's the peak of the sinusoidal distribution. So then, as you increase time, meaning the physical steps, so okay, time actually going forward in direction, that et increases, therefore peak location moves toward peak, moves toward the point where p dot x increases. So if p aligns along the x direction, it moves along the positive x direction. So in either case, meaning whether this is plus or minus, which are related by the flip of a 4 momenta, physically they correspond to the same 3 momenta physics. Is that clear what I'm trying to say? Okay, so either way, the physics is basically controlled by the same feature with the same, say, velocity or momentum, 3 momenta if you like. And then obviously it's also consistent with this analysis too, right? So I took the particle with the 3 momenta p, then here it is incoming particle, here it is outgoing antiparticle, the same 3 momenta. So this will be important. So under the flip of a 4 momenta, incoming particle with 3 momenta p vector p turns into outgoing antiparticle with the same 3 momenta. Good? So we should get this. Okay, so with that, that's the preparation now to analyze the protein. So let's do it. Good. Now, also, since we consider here only scalar field theory, right? So far we've been talking about the scalar. Then apparently so this means that invariant Feynman amplitude, or let me just write invariant amplitude A, which we used to write like this, which is a function of external momentum. In case you have n external x, is only a function of momentum squared. What do I mean by this? So this is a function which is Lorentz invariant function of momenta. And you know how to construct the Lorentz invariant function, which is basically you take some momenta, either sum or subtract, squaring it. And here, what the scalar means is that the only non-trivial object that carries non-trivial representation of the Lorentz group is this momentum. Okay, there is no other spin, polarization, stuff like that. Okay, which we haven't introduced, but if you're talking about a spin particle, then in addition to this, there's other tensorial object which can be participate in the construction of amplitude. But here, scalar means that the only non-trivial Lorentz tensor is momenta. So I just need to construct a Lorentz invariant function out of the momenta. So I'm saying for scalar field theory, therefore, invariant amplitude is only a function of momentum squared. Is that clear? Good. So what are those? I can just construct. So what are those candidate momentum squared? So here's my notation. So I can construct 1, 2. And I can take 1 and 2 as squared. I'm just gonna construct totally symmetrical way. 1, 3. So 1, 2, 1, 3 square. And so the first I can do it all the way up to S1n, which is P1 n square. You can keep going, right? So now 2, 3 is P3, P2, P3 square, all the way up to 2n 2 and square. Keep going until you hit n minus 1 n, which is n minus 1 plus the n square. So these are the complete set. Every possible thing you can imagine. Yes.
Can you please give these?
Push. Oh yes.
오른쪽에 붙는
I'm not supposed. Good. See that? Good. Can you see now? Okay, is that clear so far? Yes. Now, good. So going back to this 2 to 2. So in the case of 2 to 2, there are special names. So in the case, let's list what are the possible things. I can write down what let's do, which is P1, P2 square. I can write 1, 3, P1, P3 square. 1, 4, P1, P4 square. But by momentum conservation, 1 plus 2 should be equal to what? 3 plus 4. And then 1 plus 3 should be equal to 2 plus 4. And then this 2 plus 3. So why is that? Since I'm setting up the thing like that, I mean every momentum goes towards the vertex. So total momentum conservation that is P1, P2, P3, P4 is equal to 0. So I can use this to write this in terms of the other complementary set. Now there's a special name, and let me write out the name. So this 1, 2, or 3, 4 is called S. And then this 1, 1, 3, 2, 4 is called the T. And then 1, 4 is called U. And these variables, which are Lorentz invariant constructed as a momenta, is called Mandel's M variables. Or 2 to 2. But in general, you can also try to plug it in for general definition. Oh, I didn't mean P here. I meant S everywhere. Good. So was there a question? Was there a question? Okay. So then the point is the following. For scalar field theory, 2 to 2 amplitude will be a function of this. So generically, therefore 2 to 2 scattering, the amplitude is going to be a function of S, T, and U. However, this is over, so S, T, U is over complete set. Which means that that you need there are more than you need. Okay, so in order to show this, you can prove that S plus P plus U is the same as sum over 1 to 4 mass squared. Meaning you have 3 variables, but you have a 1 constraint. Okay, which means that this shows that there's only 2, independent variables. Yes.
What's the meaning of this S plus P plus U equal to sum of M?
The meaning of this equation, but the meaning of this equation is that even though they look like nice combinatory combinations of this momenta, but I'm saying these 3 variables S, T, U are not all independent. And the meaning of that equation is if you sum S plus P plus U using that definition, then it's the same equal to the sum of mass squared of the all external lines. M1 squared, M2 squared, M3 squared, M4 squared. The mass. Sorry, here by Mi squared, I mean Pi squared. In their mass squared. So that can be shown very easily. So let's quickly do it. So that thing can be, you can look it up. Since it's quick, let's do it. The 2 times of that is right there. So S is what? P1 plus P2 squared. But then I can also write S in the second representation, which is same as P3 plus P4 squared. So that's 2 times of S. Yes? T is 1 plus 3. Also, I can write it as a T as 2 plus 4. That's T. And then U is 1 plus 4. Again, I can also do it as a 2 plus 3. Right? So you see that in all these 3 rows, 1, 2, 3, 4 appears. Okay? So then, if you do it, obviously there are the 3 P1 squared, the 3 P2 squared, 3 P3 squared, and then P3 P4 squared. Then I can write it as a 3 times, right? 3 times summing over 1 to 4, and then Pi squared. And then there are cross terms. 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. That's complete combination of 2 times Pi dot Pj, where I'm just summing over this. Meaning not including the thing combination that has the same Pi, which is already taken into account this. Okay? On the other hand, because of this fact, sum over Pi squared is 0 by momentum conservation. So here you're gonna get sum over Pi squared 1 to 4, obviously. Square that. But also you have 2 times full combination of Pij, where again you don't include the case with the same I. So if you subtract this from there, okay, you subtract that from there, what do you get? 2 times St plus Stu, because that plus 0 is that thing, that's the left hand side, is equal to, you subtract that again, and then you only left with 2 times over mi squared, or do that squared. That's the proof. So anyway, so the point is that for scalar amplitude for scalar scatterings, this looks like maximum possible Lorentz variables, but there's one constraint. So we know that in general, now let's keep it. So now we know that the amplitude is going to be in general, or so we know that amplitude A is a function of 2 over 2 minus some variables. I'm talking about 2 to 2 scalar process. This is not fully general. For 2 to 2 scalar scattering. So for instance, we can imagine you have something like S of St or S of SU, which are related by that relationship, right? You can always train T with U using that, right? With the fixed X, and you can imagine T of U, whatever. Okay, which we will soon see examples. However, it is sometimes useful still to just use the old SPU variables. Okay, but understanding that there is just a non-trivial constraint to be satisfied. Okay, you might say, what's the usage of using redundant set of variables? Now, in physics, especially in high-energy physics, you will encounter a lot of redundancies of the description. Meaning, you're going to bring in something that is more than you actually need to describe physics. So, which is bothering, right? Why would you introduce a redundancy if you don't have to? And most of the time, the reason why you introduce actual redundancy is to manifest some of the properties. Okay, some of the properties that you really want to see. So in this case, if you just look at this versus that, obviously, if there's non-trivial symmetry which are related by SPU, and then if you express amplitude only in terms of two selected variables, right? Any such non-trivial relationship among SPU will be hidden here, right? So therefore, in that circumstances, it is actually nice trial to use all three, which will manifest some of the properties which are related by SPU exchanges. Okay. However, you have to make sure that there is a constraint. So usually, therefore, we can. Sometimes I put F5, sometimes I don't because I forget or I'm lazy. But you understand. I'm talking about the same object. So asking you, but understanding the fact that there is not a constraint. Okay. So that's what we're gonna do. But from now, I'm gonna drop this. But you understand that there is not trivial constraint among STU. Good. Now, there is a formalism, there is a language that is particularly useful to talk about this sort of object. So that's how we will talk about. Okay, any questions so far? Yes.
모멘텀을 두 개씩만 더하는 이유가 이 삼성 띠오리만 보는 건가요?
So, you mean why only square?
아니 왜 두 개씩만 더하는 거죠? Why do we sum only two momentum for each?
Oh, okay. So the question is, why did I only look at the sum of only twos rather than looking at the square of the three objects, three momenta and four? Okay. First of all, four is manifestly trivial, and then the other case, like, I just look at the three and squaring it, which by momentum conservation should equal to the other momentum square, which is a number, like fixed number rather than a parameter of the function. Is that clear? So it is. So you can look at it, but it's not a variable. It's just a constant. At least for 2 to 2. Is that clear? Yeah. Okay. Another question. If I move on. Yes.
Still parameter. I mean value even we sum two of momentum.
Say it again. I didn't catch.
So they are momentum from outer.
Yes, external legs. Yes.
Yeah. So isn't it still 그러니까 둘이 더해도 그러니까 P1 플러스 P2도 여전히 그냥 밸류 아닌가요?
It is a value. I'm viewing that as possibly tunable tunable quantity. Meaning, imagine you're an experimentalist. Okay, so the question was, I said that the square of the three objects same and the square of the other guy, which is a number. The difference between that number versus square of the two chosen momenta is that you want to check how does this as a function of those values change behave. So I can have an experimental setup, and then I can try to change P1 plus P2 value. Because this has a momenta, I can try to increase energy by changing P1 plus P2. So this is a changeable, tunable quantity. On the other hand, the mass, if I'm talking about a fixed theory with some particle with a fixed mass, there is once and for all a parameter of the theory. Parameter is to be determined once and for all as a number. But this STU are variable. I mean, it is a variable. Okay, rather than fixed constant number.
사실 아마 그 M 스퀘어랑 B 스퀘어가 같다부터 뭔가 잘 이해 못한 것 같은데.
So in the case where I'm talking about three, sum of three.
아니요, M 스퀘어랑 B 스퀘어랑 같다.
B는 뽕모멘텀이니까 당연히.
Yeah.
아, 같군요. 아, 네.
모멘텀이 아니라
Yes.
뽕.
So
아, 네.
it describes the number. Yeah. Okay.
알겠습니다.
Good. Good. Yeah.
쉘이 아닌 게 유의할 때가 있나요, 물리적으로?
The question is, can we talk about the like off-shell physics here? No. Yes. So, well, I said two things which totally consistent. So, no, in a sense that we are developing asymmetric theory here. So we're developing a particular observable, which are like one of the most important classical observable in relativistic quantum field theory. Is that I imagine I'm actually preparing a particle and then actually I create on shell and they propagate some distance. And then they collide, this is coming out something to the infinity, meaning they propagate long distance. Long distance propagation is achievable if you go on shell. Okay? On the other hand, there's off shell because sometimes some of the processes may be factorizable like this, there's some other particle intermediate, and there's something coming out like that. Okay, and sometimes these particles can be off shell. So this says yes, but they don't appear as asymptotic state. We talked about asymptotic state. So experimenters prepare asymptotic state, shoot that and observe what happens. Okay, but here I'm saying the amplitude is a function of the external momentum. And it is manifest, they are necessarily good. But option is only appears through these internal lines. Good. Another question. Okay, let's move on. All right, so we understand that much. So I haven't stated the crossing yet. So now let's build up a useful language to describe this phenomenon. So now if you look at this, S plus T plus U is equal to some constant. So this is some constant. Do you see that a plane coming out of the three-dimensional Euclidean space? It does. Okay. Oh, it does it. So good. So let's imagine I draw S, T, U, or X, Y, Z. Okay, and the equation of plane in 3D Euclidean space. So plane is obviously 2D object that lives in the 3D. Can be described as follows. So pick so say this is your plane, lovely plane, in the 3D dimensional world. So then suppose this is the normal vector, which is uniquely definable. Good. Then every vector living on here, suppose let me call that X, is normal to orthogonal to this N. So far so good? Good. So that means the equation of plane the set of X which satisfies this. However, if you look at this, obviously one of the things that solves this equation is X equals 0. Right? But the myth is that this is a plane that passes through the origin. So if you want to get the plane that is displaced by some vector A, what do? You displace every vector by A. Good. So that is X minus A is over 2 that uniform vector. Clear? So if you plug in here STU with normal vector being 1, 1, 1, you get this equation with some particular A vector. You see? This is like 2 minutes summary of what you have learned probably in high school. I don't know. I don't know about the curriculum this is, but at least when I was high school student, we had that thing. Okay. So this is the equation for plane. Good. So then we draw that. I love yellow, but there's no yellow today. That's P. So I'm gonna stick with the blue. So I'm drawing triangle, but you know what I mean. Okay. So there's that plane, which is defined by that equation. Okay? So certainly there's a displacement from the origin because of that factor, which is that exactly that contribution. So the origin here is like, well, whatever is satisfied this equation. So that origin of this plane, I mean, is 1/3 square of m squared, 1/3. Oh, that's stupid way of writing. Anyway, 1/3. So that's the origin of that plane. And then this line is when s is 0. So the entire this plane is when s is 0. Right? And then you start having non-trivial s as you go up like that. Good? And then t direction, so that point is where t is 0. So here is t equal to 0. You start having non-trivial t as you go up like that. And the u here everywhere is u is 0. So this is equal to 0. But as you go up, you're gonna get non-trivial u. Clear? Good. You see, I'm waiting for a moment. I'm using of this, but I'm failing. Oh my god! Yes. So probably I'm gonna get paid. Okay. So therefore, this plane constraint that incorporates this constraint equation. This is called Mandelstam plane. And the point is that the amplitude is a function that lives on this plane. Right? You don't like that idea? Yes. It doesn't matter. Oh, it is the truth. So the amplitude SPU in a constraint lives on this two-dimensional plane. Okay? Good. Okay. Okay. So let me skip one discussion, which you can read from the Coleman, that you can choose, a particular basis here. You can express, arbitrary vector in terms of those bases and so on and so forth. But let me skip that. Instead, let me go to the actual physics for it. Now, you can ask, what is the physical meaning of? What is the physical meaning of SMU? Okay, so far, just theoretically, formally, we know that we can define that, and then we just learned that there are some non-trivial constraints about that. So what is the physical meaning of that? Good, eventually I'm going to use it. So let's look at the process where I look at the time like that in this picture. So that describes 1, 2 coming in along the momentum direction, and then this comes out, but since I'm going against the charge flow, it's going to be antiparticle 3, and then antiparticle 4. And then also, since I have to go that way, I have to flip the sign of the P3 and P4. So this is described by amplitude with P1, P2, plus P3, P4. Okay, and that describes 1 plus 2 goes to 3 bar plus 4 bar. And again, the question is, what's the meaning of that thing? So like that, F is the first plus the second appearing in this argument. This is P1 plus P2 squared. And then if you go to the center of momentum frame, where the 3 momenta cancels out, you saw already that is ET, total energy, times 0 vector squared. And we know that this is total energy. And it is squared. But I'm gonna omit the square all the time. Okay, I have to say the million times of square. That means total energy. So the physical meaning of S in this process is total energy. So T is the first argument plus the third argument appearing in this level. So that's P1 minus P3 squared. So we look at this sort of object before. Okay, we look at the central momentum frame like that. We computed it. So if you go to the central momentum frame, we found that it is 2p squared 1 minus cosine theta. And then we decided to write it as minus of delta squared. Okay, let's continue. U is the first argument appearing in this level, which is P1 minus P4 squared. we already have done the calculation, we call it a cross momentum transfer. So in this process, F means total energy, TU means momentum transfer. Square, but once again, I'm not gonna say square all. Okay, let's continue. I don't want to stop here. Let's continue. So that's the first thing I can look at. And then let's look at the, now time goes down. So first of all, that will be 1 plus 3 goes to 2 bar plus the 1. If you read the diagram from that, right? And this will be described by the amplitude with the P1 but minus P2, P3, but minus P1. Okay? So let's compute T first. For the reason, so this T means the first plus third here appearing here, P1 plus P3 squared. Again, this will become total energy. But U, in this case, is P1 minus P4 squared. So that's going to be, say, momentum transfer S is going to be the first plus the second appearing in this level, in this language, P squared. So that will be called like momentum transfer. So if you look at it that way, now T plays the role of total energy, but SU plays the role of momentum transfer. Okay? Good. So now let's finish the one last thing. Now let's look at the I can't draw this thing, but I think I demonstrate this. So you look at that and then let the other go in. Yes? So if you do that, so we can look at 1 plus 4 goes to 2 bar plus 3 bar. And then you can compute this again. In this case, U, which is the first plus the fourth, that will be the total energy. And then S, T will be playing the role of momentum transfer. Here, momentum. So what's the point of all this long discussion? So what's the physical medium of SPO? Well, it depends on which channel you're looking at. Okay, which direction you're reading the diagram of. So if you look at that way, then S plays the role of total energy, the other two momentum transfer, which are crucially, S is positive. First of all, this should be positive. But the other two are necessarily equal less than 0. Slightly more refined way, S, which is total energy, but the minimal energy that each particle can carry is its own mass plus momentum energy. Yes? So slightly more refined statement is that in this channel, the total energy or S should be equal or greater than 2 times the mass squared. So 4 times that squared. So suppose I consider equal mass situation just for the sake of simplicity. Okay? So let's focus on the case where all the masses are the same. So then S not only being equal or greater than 0, actually it should be greater or equal to 4 times m squared of each of the particle mass. On the other hand, TU, now being the momentum transfer, should be less or equal to 0. Clear? On the other hand, if we look at the other channel, like 1 plus 3 way of reading it, T plays the role of total energy. Once again, this is going to be equal or greater than 4 times m squared. But the other two is going to be less or equal to 0. Finally, if I look at this channel, then U plays the role of total energy, once again equal or greater than m squared. But the other two, which plays the role of momentum transfer, should be less or equal to 0. I said a lot, right? In like 2 minutes. You got it so far? Yes.
Yes. Can you repeat the meaning of the channel?
Good. So good. Well, that's funny because now I will define channel. So therefore, you see from this discussion that at least in all those cases, one Mandelstam variable plays the role of the total energy. The other two plays the role of momentum transfer. So it's proper or reasonable to give a name to each of them according to that special variable. Okay? So when I look at this particular process, I'm just kind of call that process as S channel process. Because here S plays the role of total energy. Okay, which is equal or greater than 4 times m squared. Here, obviously, it makes sense to call it a P channel. And then finally, here it makes sense to call it U channel. And whenever you look at the I channel, meaning STU channel, that spatial variable is always equal greater than 4m squared. Again, I'm talking about equal mass case. Gather to necessarily less than or equal to 0. Okay, now let's draw this situation on the model template. Okay. Good. So I'm gonna draw here. So let me. This is S equal to 0 line. And I need a T. So this is my T equal to 0 line. So then T becomes positive like that, S becomes positive like that. And then here's my U equal to 0 line, and then U becomes positive like that. Okay, so I draw a model sum plane. I'm going to draw what is called now model sum keyboard plot. So what it means is let's draw a region where these conditions are satisfied. Okay, remember, if you have a situation where none of these are satisfied, that means that there is no physical process in that choice of S, T, and U. So first, let's look at the S channel. S channel means that it should have something greater than 4m squared, but the other two is like less than 0. So S should be greater than something, and then T should be less than 0. U should be less than 0. When they meet, this is S equals to 4m squared. So the S channel leaves here. Okay, on Mendelssohn plane. How about the T channel? So T gets increased, and then S should be less than 0, U should be less than 0, and this point is the T threshold. So we're gonna call this special point a threshold. So for instance, you can threshold. U help me threshold. U?
No.
No U?
No you.
Very good. Okay, there's one person that's useful in my crisis. S threshold, okay? S channel threshold, T channel, and so T channel lives here. And now you can guess U channel lives here, and then this is U threshold. This is where U channel is. Okay, good. Now we prepared enough to be able to state the crossing. But first of all, if you are somewhere else here and there's no other possible physical process happening. Okay, take the function A. We're talking about function A, STU. Oh, STU, and then we're gonna look at the regime of some values S and TU. Okay, I'm saying this, yes, there's a physical process associated with it. And it's nothing but that process, not the other ones. If I go to the region here, there's a physical process, which is that P channel process that I will draw there. If you go here, there's also the physical process. But if you're just drawn somewhere here, there is no physical process that can ever possibly happen. So therefore, in that sense, this is like physical region for STU processes, STU channel processes. Okay, now I'm gonna say in word, and then I draw some arrows. Suppose you choose STU such that you are somewhere here. Okay, some physical process happening. 1 plus 2 meets, and then spits out antiparticle 3, antiparticle 4 with some energy. Okay, and you're happy. So you constructed a function of the real momenta that corresponds to the actual physical process. All right. Now, what you do is the following. Now you do that function, You started out as an actual fixed number, but now you can express amplitude as just actually arbitrary momenta. And not only that, now you view that as a function of a complex momenta, SE. Okay? So if you're given sine of x, yes, first you can look at like sine of 2 pi over 3, aha, and then you do sine of x. Yes, I view this as sine of x is a real variable. Now I'm going to view this as the sine of complex number x. Okay, you learn how to do computation of that kind of stuff if you know how to go into the complex way and then do the constant integration. Okay, so that's what we're kind of doing. So you first determine this with a fixed number, you view that as now a function of momenta. Not only that, now you view this as a function of a complex momenta STU. All right. So once you know that, you ask, okay, can I analytically continue from this region to that? Or can you go from here to there? Or can you go from here to there? Through the analytic continuation, which I will demonstrate in one very easy case in a minute. So the point of this discussion is that a single function eventually, even though you may construct from one particular physical process, but now you can just construct a single function called amplitude, which is analytic almost everywhere except isolated poles and branch curves. So we haven't gone through the branch curve story at all, which we need the loop diagrams. But anyway, for now, you can view this as a function. Remember, the characteristic of this function looks like P1 plus P2 squared minus like M squared I, something like that, right? We haven't looked at all these kind of functions so far. This is the function with the pole, right? So this is an analytic function other than poles. Those are called meromorphic functions. Once you have a meromorphic function, you can analytically continue the validity, region of validity from one piece to another and to another. Once you can do that, once you can travel from the one region to the other, then a single function now you're given God-given function, you can zoom in here to describe this physical process. Or you decide to zoom in here, you can discuss the T-channel physical process. And then you can zoom in here to describe U-channel processes. So a single function is managed to capture or describe 3 distinct physical processes. Okay? So this feature is known as crossing property. You just cross out, meaning you just go from one channel to the other by analytic continuation. So here, a key point is that a single function, in the case of 2 to 2, a single function, meromorphic function of STU, actually describes 3 different processes. And we're going to talk about now CPT, and we will get 3 more other processes that single function can describe. So a total 6 eventually. But for now, it's 3. Okay. So far, any question? Yes.
ST and your real variables. So how do we discuss?
So the question is, STUR, which variable is that?
Real value.
Oh, good. So that's what I said here. That suppose you're okay. Let me erase something and then address the question. So here is a quick reminder and illustration point. Okay. So we look at some point some amplitude. Let me just write that looks like P minus P3 squared minus M squared I. I mean, if you don't remember where that comes from, that's fine. But you haven't seen something that looks like this, at least. Okay. And this, remember, this is minus delta squared. So that is like minus I over delta squared plus M squared. And this obviously is not T. So let me just rewrite again. I over T plus M squared. Yeah. Okay, T is a real number, like 20 GeV. But instead of 20 GeV, let me read that as a function of a T. First of all, time. However, if you just read it as the only function of real value, okay, you can read it, but there's a benefit of viewing this as a function of a complex variable T. The benefit was that all of a sudden you start recognizing non-trivial, singularity structure. So if you if you say on the real line of axis t, obviously you never recognize those things. But if you do this as a function of complex variable t, then you start seeing this non-trivial physical point, meaning the singularities, which encode the physical meaning with it. So we have done that already, right? And then we computed the complex concept of distribution as well as others. That's what I'm saying. So a given process will give you 20 GeV, but one promotion is I view this as a function of t, or real number. A second time promotion, I actually view this as a function of complexity. Then you see these isolated poles, so it can be very more promotion. Okay, another question before actually demonstrate this with the concrete amplitude. Okay, so let's do it. Okay, so one thing that I want to say is that so you can ask what happens if I don't assume it's all like same as base cases, right? But you see, that direction corresponds to taking super high energy regime because S becomes larger than threshold. You can go above the threshold if you have a more energy than just reference energy. So that direction is high energy regime. This regime is high energy regime, and that regime is high energy regime in each of the physical processes. So if you take the case where mass are not all the same, but then you see asymptotically in the high energy regime, mass effect is negligible, right? So then asymptotically you asymptote to this nice looking figure, but there might be modification of that region. But asymptotically you go that picture, you can change whatever, you can asymptotically go that, like that. So the point is that no matter what you do, this physical region will never overlap. Because if you have some process, there's no sense that you can say, oh, this is actually either 1 + 2 going to something and simultaneously 1 + 3 going to something. Such a thing doesn't exist in the physical world. Okay, so that's one big point. Second big point is the following. Now, again, A of STU. So, nice property number one is, so let's look at the 1 + 2 goes to 3 bar plus 4 bar. So look at that arrow. So suppose if 3 bar is the same as 4 bar, they are identical particles. Okay. Then you see that the T and U are the same has the same meaning, right? They're identical. So that means that in this case, the amplitude will satisfy as a function of these variables S and UT. So you have a certain symmetry property if you like. And you can keep going. For instance, what if 2 bar is the same as 4 bar, for instance? Then what do you expect? Now you're looking at P channel, and then with S and T being momentum exchange. But you should have this both Einstein statistics, so to satisfy the property, for instance. Okay, so in this language, I'm just demonstrating in this language, then you can also learn extra symmetry properties in terms of STU variables. Okay, of course, we already learned all of that in explicit computation, but I'm just phrasing in this language. Okay, so super quick demonstration of this crossing symmetry. Let's look at this process that we already talked about. Let's look at concretely, first of all, that let's compute it. P1, P2 coming in, and then P1 prime. Let me just write it as P3. P4 coming up. So this corresponds to N pi and pi. And then there were another diagram that we had to take into account. So if you remember, that was that P1, P2, P3, P4. So here, intermediate line has P1 plus P2. Here, intermediate line has, let's see, so that comes out, coming in, that's something the same as that. That means this is P2 minus P3, which is the same as what? Anybody? P2 minus P3 is equal to what? P1 plus P2 to, okay, in this case, I have to look at it slightly different way. So P3, let P4 equal to 0. So 2 minus 3 is equal to minus P1 minus P4. Okay? Good. Now you know how to compute this amplitude, which we already did it. So the amplitude in that n pi channel is equal to up to, so let me just bring it proportionality factor, up to P1 plus P2 squared minus, this is nuclear mass, the capital M, I plus. And then the second diagram, which is P1 minus P4 squared. Capital M per I. Let's see. Yeah. So we can write this as what? S minus capital M squared plus U minus this squared. If you ever remember, we talked about the fact that this channel describes non-trivial pole line contribution. We talked about this corresponds to non-trivial momentum transfer channel. And we already talked about in this S channel diagram, S channel process, S plays the role of actual initial total energy, U plays the role of momentum transfer. So it all fits in. Now, let's read the diagram on the other hand from the top to bottom, like that. Okay? So now I'm looking at P channel process. Okay? So now this describes pi goes to n bar. So if you do that, on the other hand, now you have to read as a P. So in this case, amplitude has a P1 but minus P2, and then plus P3 and then minus P4. Right? Because I'm reading that way, so I have to take this to be positive, this to be minus of the argument. Okay, so in this case, what happens? So then if you read that way, now, like I told you, you have to flip the sign of, so flip the sign of P2 and P4. And here too, you exactly do the same thing, but flipping sign of P2 and P4. So take this thing, take this thing. So let me just do that replacement. That means that previous P2, I have to do it minus P2. Previous P4, I have to do it minus P4. Yes.
The sign of P3 will be changed.
Yeah, P3 also have to be flipped backwards. Meaning, yeah, I have to do it plus P3. I didn't say that because the P3 doesn't appear here, but you're right. But yes.
So why the sign of P4 have to be changed?
Oh, actually, no. Sorry, hold on a second. Yeah, actually, no. P4 doesn't change, you're right. Okay, let's clarify again. How do we do it? First, we take this with everybody coming in, right? And if you do this, whatever comes out, I have to read as minus of the data segment. So here, 2, 4 should be minus, 1, 3 should be plus. Here, 1, 2 plus should be plus, and then 3, 4 should be minus. In both of the T channel and the S channel, P4 has always been minus. So I don't, compared to S channel computation, I don't have to flip the sign of P4. That's why you said. Compared to S channel, here I have to flip the sign of a 2 and 3. Which one turns from external to the incoming, outgoing from the incoming. 2 turns from the incoming to the outgoing. I have to flip the sign. Okay. So let's just use that rule and take this external amplitude. Okay. Take this external amplitude. Let me flip the sign properly. So what I get is P1 minus P2 squared. By flipping that. And then here I'm not going to flip. The P4 has been already done. So in this case, 1 minus 2 plays the role of yes, S again minus M squared. It's the same function. U m squared I. But now if you recall, when we discussed the pi goes n bar, two physical properties that happened in the pi goes n bar was two Yukawa-like physics. One was direct, the other was cross. Both were energy dependent range. And then remember in T channel, P plays the role of total energy, as U plays the role of momentum transfer. So indeed, if you just do what crossing symmetry tells you to do, you need to get two momentum transfer physics, which are Yukawa-like and cross Yukawa-like, with energy dependency. Okay, so indeed, you see, if you look at these two, they are the same function, right? Function of STU, but interpretation changed. Here, S is total energy, U is the momentum transfer. In T channel, both S and U are momentum transfer. Okay, so this is explicit demonstration of crossing symmetry at tree level. Okay, but this is true regardless. That's the end of crossing. I'm gonna move on to the CPT, which is quicker to say. But question before. Yes.
Can I be channel like catchment process?
Sorry, your question is. Sorry, say that again.
My question is related with the meaning of the channel.
Channel is the name given to a process where if S plays a role, so in that physical process, if S plays a role of total energy, I just call that particular physical process to be S channel process. Because just to remember that in that process, S plays a role of total energy, the other is momentum transfer. If you look at the physical process where T plays the role of total energy, you can just call that particular physical process to be a T channel process, so that you can remember. And U channel likewise. So here I will call the S channel process, and where S plays the role of total energy. Here also T plays the role of total energy, so I call T channel process, where both S and T plays the role of the momentum transfer. Okay. So I analyze here like S and T and U, different three processes, and only one of them plays total energy being positive or greater than or equal to 4m squared. The other two plays the role of momentum transfer, which should be less than or equal to 0. That's why I draw this Mandelstam cable plot. Okay, think about it and let me know if that wasn't satisfactory. Let me take like 30-second pause. If you have any question or if you are lost, let me know.
저희는 삼각형 바깥쪽인 이유가
Yes.
모멘텀 트랜스퍼가 마이너스 델타 제곱인데 델타가 실수여야 돼서
Yes.
그게 음수가 되어야 하기 때문에 바깥 부분인 거죠.
That's right. Yes. Because already it looks like P2P squared, where P is actual momentum, so P squared is positive, and then the parenthesis 1 plus minus cosine theta, but cosine theta is bounded by 1, so it already is positive. Yes, that's correct.
야되는 이유가 있는 거예요.
The question is why it should be crossing symmetric. Is that your question?
Is there any fundamental reason why the crossing principle should move?
Good. So if your question is whether there's like mathematical proof, here is the relativist quantum field theory, and under what conditions amplitude must be crossing symmetric, or it should have like crossing property. I don't know the general proof. Here I just demonstrated for scalar field theory, and I know it can be extended to the Fermion, vector boson, and so on, including even loop level. However, if you ask whether there is a fact that every quantum field theory needs to satisfy, the answer is no. And in fact, there is a famous process. So suppose you have a particle that carries electric charge. That's called electron. Suppose you have another particle that carries magnetic charge. So like divergence of B is not equal to 0. You might say, what kind of crazy thing is that? But a lot of quantum field theory actually makes a prediction that such thing exists. You can write down solution. Okay, so the magnetic monopole is ubiquitous in quantum field theory. And then if you try to ask, okay, let me take the one electron and the one monopole and magnetic monopole and let's smash them together. Let's compute the scattering process. And this S matrix doesn't have a crossing symmetry. Okay, but for very subtle reason. And we don't have a full understanding of this physics. This is still contemporary physics research question. Any other question? Okay, crossing symmetry in 7 minutes. No, what am I talking about? I already spent like 1 hour talking about crossing symmetry. CPT. Okay, so CPT. Symmetry. So fact number 1. Again, I'm talking about scalar QFT. Right? And entire amplitude is a function of momentum square, like S12, S13, we talked about this, right? Therefore, A is invariant under take momenta of every particle and flip the side. For all, so what I'm saying is here is take an amplitude. Every possible amplitude that it can come from a given scalar QFT. Flip the sign of the four momenta for all particles external lines. And I'm saying the amplitude is invariant under that. Is that clear? Okay. So consider arbitrary variable like ij, which you have pi plus bj. That was the definition of it. But then if I flip the sign of that thing, what happens? Like minus pi minus bj squared, which is obviously the same as ij. So nothing changes. So amplitude is manifest invariant under that preparation. And claim number 2, statement number 2, that is pi goes to minus pi for all particles is CPT transformation. Hence the fact. Let's see. Okay, so how do I see that? First of all, you already recall my discussion at the beginning of today's lecture that under this incoming particle with the momentum p goes back and forth, outgoing antiparticle with the same momentum p. Right? We talked about this in detail. Now, obviously, this part, particle goes to antiparticle, that's what phi does. Right? And incoming to the outgoing vice versa is partly what t does. Because if you were coming in video, if you run the time backwards, you're coming up. Right? However, t also flips, but t also flips the p 3 vector to minus 3 vector. Why is that? Because so p is proportional to, just think about the non-relativistic case, velocity. Velocity is the derivative of time over the 3 vector, and under t, x doesn't flip, the p flips, therefore p flips. But then I said that p goes to p. But we know that under parity, it also flips x to minus 3. So if you combine p with p or p with p, then 3 momenta doesn't flip. So this is not just p, but the last part, the resist, can be summarized as the effect of a p times t. Okay. Another quick way of seeing it: if you have a quantum field which has alpha e to the minus pi p dot s, theta dagger e to the plus pi p dot s. So if you do the p goes to minus t, this can be compensated for by x4 vector flipping minus b itself. Right? So if you flip the p to minus b, you can compensate with that. Meaning you can read as if it's x flipped. But this is nothing but flipping the t as well as 3 vector x, which is t times p. But also you go from here to there. So from the particle to the antiparticle, that's C. Okay? So flipping the momentum for every particle is like applying CPT on the theory. And I told you that the amplitude doesn't change, so there is a CPT invariance. But this is a deeper fact. So here, this is a quick demonstration for scalar field theory, but this is a deeper fact, and I do not know the fully general proof, but I know it exists. I can learn and teach you possibly later. But let me quickly say one more thing in 2 minutes. So remember, crossing buys you. So given this master function of STU, let's just talk about two cases for now. Given STU function, which now we understand that it is just the some analytic function modulo singularities. This tells you that 1 plus 2 goes to 3 bar plus 4 bar, which is called S channel. E channel 1 plus 3 goes to 2 bar plus 4 bar, and U channel 1 plus 4 goes to 2 bar plus 3. So now crossing allows you to say that the single function takes care of this. Now CPT, what it does is that you flip, P to minus P, but that's the same as flipping incoming to the outgoing, the particle to the antiparticle. So let's apply CP to each of them. That means that I make 3 incoming but remove the bar. So it becomes 3 plus 4 goes to 1 bar plus 2 bar. Is that clear? Outgoing antiparticle becomes incoming particle. Incoming particle turns into outgoing antiparticle. Okay? I told you that's what this CPT does. And then also CPT of that, the second thing is 2 plus 4 goes 1 bar plus 3 bar. Finally, 2 plus 3 turns into 1 bar plus 4. So single function. Crossing allows you to take care of this. If you further have a CPT, which you does, also take care of these 3 extra. So combining with the crossing and CPT, single function manages to describe 6 different quantities by looking at the different regions. This corresponds to the different actual regions. Here S, here T, here U. But this corresponds to the same point in the Mallet-Cable plot. Because, like I told you, if we just split the thing, it's exactly the same S value. Right? The actual S value has not been changed under the CPT transformation. So CPT just goes back to itself. But crossing moves around by analytic continuation. Okay, now last statement is that this is actually very powerful statement. It says in a given local quantum field theory that satisfies Lorentz invariance and it satisfies what's known as spin statistics theorem, which is another very deep fact, meaning spin half means fermion, spin 1 means boson, the relationship between spin and statistics, which we haven't discussed, but nevertheless there's such a thing. So any quantum field theory with a Lorentz invariance and spin statistics theorem, every such quantum field theory satisfies CPT invariance. Okay, so it's a deep fact. Okay, so that's the end of today's discussion. Next time we will turn the F matrix into cross section and the decay rate. Okay. If you have questions, I'm happy to address outside of the lecture room. So I just
네, 그냥 종료.
okay.